Breaking news in the fight against fatty liver disease, a condition affecting nearly a quarter of the global population. Scientists have made a groundbreaking discovery that could lead to a potential new therapy, offering hope to millions of people worldwide who are at risk of liver failure. As we delve into the intricacies of liver disease, it becomes increasingly evident that the relationship between NAD+ levels and liver health is a complex and multifaceted one. NAD+, or nicotinamide adenine dinucleotide, is a crucial coenzyme that plays a pivotal role in energy production, DNA repair, and inflammation control. In the context of liver disease, NAD+ levels have been found to be significantly depleted, particularly in conditions such as non-alcoholic fatty liver disease, LD, and non-alcoholic steatohepatitis, NASH. This depletion is not merely a consequence of liver damage, but rather a contributing factor to the disease's progression. NAD+ is essential for maintaining the integrity of cellular energy metabolism, and its decline can lead to a cascade of events that ultimately result in liver fibrosis and cirrhosis. Furthermore, NAD+ has been shown to play a critical role in DNA repair mechanisms, which are essential for maintaining genome stability and preventing the accumulation of mutations that can lead to cancer. In the liver, NAD+ is involved in the repair of DNA damage caused by oxidative stress and other forms of cellular stress. When NAD+ levels are depleted, this repair process is compromised, leading to the accumulation of DNA damage and the activation of pro-inflammatory pathways. The relationship between NAD+ levels and inflammation control is equally significant. NAD+ has been shown to modulate the activity of various inflammatory pathways, including the NF-κB and JNK pathways, which are involved in the production of pro-inflammatory cytokines. In the liver, the depletion of NAD+ can lead to the activation of these pathways, resulting in the production of pro-inflammatory cytokines and the recruitment of immune cells to the liver. In summary, the relationship between NAD+ levels and liver disease is a complex one, with NAD+ playing a critical role in energy production, DNA repair, and inflammation control. The depletion of NAD+ in liver disease is not merely a consequence of liver damage, but rather a contributing factor to the disease's progression. As we continue to explore the intricacies of NAD+ metabolism in the liver, we may uncover new therapeutic strategies for the prevention and treatment of liver disease. The discovery of ACMSD inhibition as a potential therapeutic approach for MASLD and MASH marks a significant breakthrough in the field of liver disease research. By inhibiting the enzyme ACMSD, researchers have found a novel way to restore NAD+ levels in the liver, thereby mitigating the progression of these devastating diseases. The mechanism of action of ACMSD inhibition is rooted in the enzyme's role in tryptophan metabolism. ACMSD is responsible for converting tryptophan into kynurenine, a process that ultimately leads to the depletion of NAD+ levels in the liver. By inhibiting ACMSD, researchers have found that they can increase NAD+ levels, thereby restoring the liver's energy metabolism and reducing inflammation and fibrosis. The results of the study are nothing short of remarkable. In mouse models of MALD and MASH, ACMSD inhibition was found to significantly increase NAD+ levels, reduce inflammation and fibrosis, and even reverse the progression of liver disease. These findings suggest that ACMSD inhibition may be a viable therapeutic strategy for the treatment of MASLD and MASH, and potentially even other forms of liver disease. Furthermore, the study's results have significant implications for our understanding of the pathophysiology of MASLD and MASH. By identifying ACMSD as a key player in the development of these diseases, researchers have opened up new avenues for investigation into the molecular mechanisms underlying liver disease. This knowledge will be crucial in the development of new therapeutic strategies and the improvement of existing treatments. The potential of ACMSD inhibition as a therapeutic approach for MALD and MASH is vast, and its implications extend far beyond the treatment of these specific diseases. By targeting the underlying molecular mechanisms of liver disease, researchers may be able to develop new treatments for a wide range of conditions, from fatty liver disease to cirrhosis and beyond. As we continue to explore the potential of ACMSD inhibition, we may uncover new hope for patients suffering from these devastating diseases. The significance of the findings in this study cannot be overstated, particularly in the context of current treatment options for MASLD and MASH. Currently, there is only one approved treatment for MASLD and MASH, and it is often ineffective in reversing the progression of these diseases. The majority of patients with MASLD and MASH are left with limited treatment options, and their disease often progresses to cirrhosis and liver failure. In contrast, the findings of this study suggest that ACMSD inhibition may offer a novel and effective treatment strategy for MASLD and MASH. By restoring NAD+ levels in the liver, ACMSD inhibition has been shown to reduce inflammation and fibrosis and even reverse the progression of liver disease. This is a significant breakthrough, as it offers hope for patients with MASLD and MASH who have been left with limited treatment options. The potential impact of these findings on patient outcomes is substantial. By providing a new and effective treatment strategy for MASLD and MASH, ACMSD inhibition may improve the quality of life for patients with these diseases. It may also reduce the risk of progression to cirrhosis and liver failure and improve survival rates for patients with MASLD and MASH. Furthermore, the findings of this study may also have implications for the prevention of MASLD and MASH. By identifying ACMSD as a key player in the development of these diseases, researchers may be able to develop new strategies for preventing the progression of liver disease. This could involve the use of ACMSD inhibitors as a preventative measure for patients at high risk of developing MASLD and MASH. In conclusion, the findings of this study are significant and have the potential to revolutionize the treatment of MASLD and MASH. By providing a new and effective treatment strategy for these diseases, ACMSD inhibition may improve the quality of life for patients and reduce the risk of progression to cirrhosis and liver failure. As we continue to explore the potential of ACMSD inhibition, we may uncover new hope for patients suffering from these devastating diseases. The liver plays a critical role in energy metabolism, and disruptions to this process can have far-reaching consequences for overall health. In the context of liver disease, metabolic pathways are often dysregulated, leading to the accumulation of fat and the development of inflammation and fibrosis. One key player in energy metabolism is the enzyme ACMSD, which is involved in the breakdown of tryptophan and the production of NAD+. As we have discussed, ACMSD inhibition has been shown to increase NAD+ levels and reduce inflammation and fibrosis in the liver. This suggests that ACMSD plays a critical role in energy metabolism and may be a potential target for drug development. Furthermore, the liver's metabolic pathways are intricately linked to its role in detoxification and the regulation of glucose and lipid metabolism. Disruptions to these pathways can lead to the accumulation of toxic substances and the development of metabolic disorders, such as insulin resistance and type 2 diabetes. The importance of ACMSD in energy metabolism cannot be overstated. By regulating the breakdown of tryptophan and the production of NAD+, ACMSD plays a critical role in maintaining the liver's energy balance and preventing the accumulation of fat. This makes ACMSD an attractive target for drug development, particularly in the context of liver disease. In fact, the development of ACMSD inhibitors may offer a novel approach to treating liver disease. By inhibiting ACMSD, researchers may be able to increase NAD+ levels and reduce inflammation and fibrosis in the liver, thereby improving liver function and reducing the risk of progression to cirrhosis and liver failure. The potential of ACMSD as a target for drug development is vast, and its implications extend far beyond the treatment of liver disease. By regulating energy metabolism and preventing the accumulation of fat, ACMSD inhibitors may also offer a novel approach to treating metabolic disorders, such as insulin resistance and type 2 diabetes. As we continue to explore the role of ACMSD in energy metabolism, we may uncover new hope for patients suffering from these devastating diseases. The effects of ACMSD inhibition on NAD+ levels, inflammation, and fibrosis in mouse models of MASLD-MASH versus human liver organoids are a crucial area of investigation. By comparing and contrasting the results of these studies, we can gain a deeper understanding of the mechanisms underlying ACMSD inhibition and its potential as a therapeutic strategy for liver disease. In mouse models of MASLD-MASH, ACMSD inhibition has been shown to significantly increase NAD+ levels, reduce inflammation, and reverse fibrosis. These findings suggest that ASMSD inhibition may be a viable therapeutic strategy for treating mast-cell MASH in humans. However, when human liver organoids were used to study the effects of ACMSD inhibition, the results were somewhat different. While ACMSD inhibition did increase NAD+ levels and reduce inflammation, the effects on fibrosis were less pronounced. This suggests that human liver organoids may not be an entirely accurate model for studying the effects of ACMSD inhibition in humans. One possible explanation for these differences is the unique metabolic profile of human liver organoids. Human liver organoids are derived from primary human hepatocytes and are maintained in a 3D culture system, which allows for the study of liver function and disease in a more physiologically relevant manner. However, this also means that human liver organoids may have a different metabolic profile than mouse liver cells, which could affect the response to ACMSD inhibition. Another possible explanation for the differences between mouse models and human liver organoids is the presence of genetic and epigenetic factors that are unique to humans. Mouse models of mast-cell MASH are often generated using genetic engineering techniques, which can introduce mutations or other genetic alterations that are not present in humans. Human liver organoids, on the other hand, are derived from primary human hepatocytes and are therefore more representative of the human liver. In conclusion, the effects of ACMSD inhibition on NAD+ levels, inflammation, and fibrosis in mouse models of mast-cell MASH versus human liver organoids are complex and multifaceted. While mouse models have provided valuable insights into the mechanisms underlying ACMSD inhibition, human liver organoids offer a more physiologically relevant model for studying the effects of ACMSD inhibition in humans. Further studies are needed to fully understand the differences between these two models and to determine the potential of ACMSD inhibition as a therapeutic strategy for liver disease.
Technical summary. This presentation has provided an overview of the current state of research on metabolic dysfunction-associated steatotic liver disease, LD, and metabolic dysfunction-associated steatohepatitis, MASH, including the role of NAD+ levels, ACMSD inhibition, and the potential of ACMSD as a target for drug development. The presentation has also discussed the use of mouse models and human liver organoids as tools for studying the effects of ACMSD inhibition on NAD+ levels, inflammation, and fibrosis. Key findings. MALD and MASH are complex diseases characterized by the accumulation of fat in the liver, inflammation, and fibrosis. NAD+ levels are depleted in MASLD and MASH, and restoring NAD+ levels may be a viable therapeutic strategy. ACMSD inhibition has been shown to increase NAD+ levels, reduce inflammation, and reverse fibrosis in mouse models of MASLD MASH. Human liver organoids may not be an entirely accurate model for studying the effects of ACMSD inhibition in humans, due to differences in metabolic profile and genetic epigenetic factors. Conclusion. The research presented in this summary highlights the complex and multifaceted nature of MASLD and MASH and the potential of ACMSD inhibition as a therapeutic strategy. Further studies are needed to fully understand the mechanisms underlying ACMSD inhibition and to determine its potential as a treatment for MAD and MASH. Intellect Cascade. This content is the product of Intellect Cascade, a research product of Big Blue Ceiling. Intellect Cascade is a cutting-edge research platform that utilizes advanced artificial intelligence and machine learning algorithms to analyze and synthesize complex data from various sources. Big Blue Ceiling is a leading research organization dedicated to advancing the field of medicine and improving human health.